We will complete week 5 of differential equations with the method of partial fraction expansion, which in some applied situations you might encounter. And basically this is just an introduction or a recap on partial fraction expansion, and we will use it for our use in differential equations. So let's say we have t squared plus 3t plus 2 times dx dt is equal to 1 over 5x. Now the independent variable here is t and the dependent variable is x, so I would like a solution in the form of x of t. Well, let's rewrite this out. So we have dx dt is equal to 1 over t squared plus 3t plus 2 times 1 over 5x, and we see that this is in the form of a differential equation that we can use separation of variables on. So we move everything with the dependent variable to the left and the independent variable to the right. So we get 5x dx is equal to 1 over t squared plus 3t plus 2 times dt. And this is the separation of variable part. Now we know if we want to solve this, we write 5x dx is equal to 1 over t squared plus 3t plus 2 dt. Now this is not a function we can integrate immediately. We need a couple of steps. We are going to apply partial fraction expansion, where we have, we know that, well, let's take an intermediate step. T squared plus 3t plus 2 can be written as t plus 2 times t plus 1, which means that 1 over t squared plus 3t plus 2 can be written as some fraction a over t plus 2 plus some fraction b over t plus 1. And this is partial fraction expansion, but we need to find a and b. Well, to find a and b, we rewrite the right-hand side to a single fraction with a common denominator. So we write this as a times t plus 1 divided by t plus 2 times t plus 1. So essentially I've multiplied this fraction by t plus 1 over t plus 1, which is equal to 1, plus b times t plus 2 over t plus 1 times t plus 2. So now these two fractions have the same denominator, which means I can group them together. A times t plus 1 plus b times t plus 2 divided by t plus 1 times t plus 2. And of course, multiplying these, we end up with a times t plus 1 plus b times t plus 2 divided by this denominator, t squared plus 3t plus 2. So if this fraction is equal to this fraction, I know that because the denominators are already equal, that 1 must be equal to a times t plus 1 plus b times t plus 2. And let's write out this right-hand side. This is equal to a times t plus a plus b times t plus 2b. I group the terms with t together. It's equal to a plus b times t plus a plus 2b. Now on the left-hand side I only have 1. I have 0t. So a plus b is equal to 0, and a plus 2b is equal to 1. Now this is a set of two equations with two variables, and we know how to solve these. What I'm going to do is subtract the first from the second, and I end up with b being equal to 1. And if b is equal to 1, then a must be equal to -1. So 1 over t squared plus 3t plus 2 is equal to 1 over t plus 2, minus 1 over t plus 2 plus 1 over t plus 1. This is partial fraction expansion, which we will also need in the Block 8 course on automated flight. So we use this to say, well, this one we can simply calculate. 5 over 2x squared is equal to, well, this, but we couldn't calculate this. But if we now look at -1 over t plus 2 plus 1 over t plus 1 dt, we can now integrate this, because this is the sum of -1 over t plus 2 dt plus 1 over t plus 1 dt, because of the sum rule for integration. And these two we can calculate. This is equal to minus ln t plus 2, the absolute value of t plus 2, plus the ln of t plus 1, plus some integration constant, which I'll call C1. So we have 5 over 2 x squared is equal to minus ln t plus 2 plus ln t plus 1 plus C1. Now, to find our solution x of t, I multiply this by 2 over 5, so x squared is minus 2 over 5 ln t plus 2 plus 2 over 5 ln t plus 1 plus, yes, and I could now write 2 over 5 times C1, but 2 over 5 times C1 is also a constant, so I'm just going to replace this by C. Okay, if x squared is equal to that, then we find that x is the square root of what we find here, or x, and let's be complete, x of t is this, or x of t is equal to minus the square root of what we find here. So our solution for x squared, we put in that root there, and we put it in that root there. So we have two solutions. So here we started with a differential equation where we kind of got stuck at this point. Using partial fraction expansion, we can replace that fraction by the sum of two partial fractions, which means we can integrate it, which means we can find our solution. And that concludes an example on using partial fraction expansion to solve differential equations. So we saw direct integration, separation of variables, and partial fraction expansion. We will work with this for this week, and in the next weeks we'll focus more on linear differential equations, first and second order, and how to solve them.